Hi, this is David from Electric Teaching, and I'm going to introduce Taylor Polynomials centered at 0, also known as Maclaurin series or Maclaurin polynomials. But I believe the best place to start is something familiar. Hopefully you've seen geometric series and as they go out to infinity getting a result. And that's a good place to start. Right here I have a geometric series with an r equal to 1/2. And since r is less than 1, or the absolute value of it is less than 1 is technically the rule, then we will know it converges. And this is what the expanded part looks like. If we were to plug and chug, as I like to say, or substitute and evaluate, but I'll say plug and chug. So n equals 0, plug that in, we're going to get a 1. And then with the series, we're going to add n equal at 1, and we're going to get a half, and the same thing at n equal 2, we get a fourth. And if you let that go to infinity, this will sum to 1 over 1 minus your r. My r is 1/2, so 1 over 1 minus 1/2 equals 2. Now, we could think about this first three terms, these first three terms right here, the 1, the 1/2, and the 1/4, all added together, and we do have an approximation for the final value of 2. We're not very close to it, but this would be a way to approximate it. The further I get out there, I can approximate the value better. And that's the main idea. That's the main idea. So let's take a look at this geometric series. And I want to plug and chug a 0 here. Plug and chug a 0, we're going to get r to the 0. And then we're going to add plug and chug a 1, r to the 1, and continue this on, r to the 2, and r cubed. And again, this goes on forever. And when we get to the final result, it's going to be 1 over 1 minus that r value, our ratio. Okay, or our rate in between, or multiplier in between, or ratio. And that's the main idea here then. I want to look at this and compare it to this idea. So we can see that we end up at this exact value. If we use an infinite series, we'll end up at an exact value. If we use a finite partial sums version of it, we'll get an approximation. And I want to show this to you, okay? So I'm going to take in this first approximation here and put it in function terms. So I want to look at that first 1, 2, 3. We'll go out to r squared here. So this will be n equal 2, and that means we're going to get a second degree polynomial out of this. We're going to get a second degree polynomial. R to the 0 is 1. R to the first we'll call x, since we're doing this in function terms. And then we're going to go x squared for the r to the squared. And we should see that this is very close, a close approximation graph-wise to the function 1 over 1 minus x. And I've got that set up. I want to show you what that looks like. So here in the Desmos graph, forgive me for using Desmos, I like this program a lot. Kudos to them, props to them. If you don't know how to use Desmos or haven't been familiar with it, please familiarize with them. It's a great tool. And you can see that the graph in red is the 1 over 1 minus x. It's over here as well, but I want to focus right in this area and zoom in just a bit here. And you can see that we are really close. We are really close to the cubic graph coming through here, to the cubic graph right over here. Oh, sorry, I was actually comparing it to the x squared graph at first. So let me first do it to the x squared graph and just see how close it is. Okay, so here's the 2 degree polynomial. Okay, and you saw a little bit, because I did have it set up already, to if I expanded it out to the cubic, it would even be closer to the original graph, the graph at the end. And this is only close to 0 right now. I want to mind you that we are keeping it between basically about -1 and 1, that it stays pretty close. Right now with the second degree, between -1/4 and 1/4, it's really close. And even the output values that are as well very close. Okay, so with that idea, let's take a look at something called a power function. This is going to be a power function now. So a power function has the same idea, but we're going to put coefficients in front of this. We're going to put coefficients in front of the geometric series. So we would say that a power function is a summation from 0, n equals 0 to infinity, and we're going to put a sequence to be the coefficients. These are just the coefficients on the x's, x squareds, on all the terms. Okay, and then we're going to have this x, just like we did before with the r, but x to the n. And this is a power function. And if we were to take a look at this power function and start to expand it, we would get a sub 0, okay, x to the 0 plus a sub 1 times x to the first plus a sub 2, again, just the coefficient. Keep in mind, these are just numbers, coefficients, if they were going to follow a numerical pattern here with the sequence. And that's all they are. They're the coefficients to this polynomial that I'm building. I'm at a quadratic polynomial now, and I'll continue it one more time. Hope it doesn't go off the recording here. Squeeze it in to the third cubic. I hope that's on the recording. It looks like it's right on the edge. Okay, and remember, this goes dot, 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 plus dot, 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 dot. This is an infinite series, but I want to look at a partial sum of them to approximate the to have an approximate function, to create an approximation to be equal to a function. I'm sorry, that didn't come out well. Let me keep going with this here. So let's first plug and chug. Let's first take a look at this as a function. So I'm going to squeeze in the function notation over here on the side. So this is f of x, and I want to look at f of 0 right off the bat. Let's see what happens when we look at f of 0. I'm going to jump over the series right here and kind of jump into this idea that if I plug and chug x equals 0 all the way across, x equals 0 all the way across, don't forget x to the 0 here is a 1. This is just a 1. Remember up here too as well. R to the 0, that was just a 1. Remember it became a 1. If I plug and chug f to the 0, this term, the linear term, the quadratic term, the cubic term, and all the other terms all plug and chug with the 0, they all go bye-bye. They're all going to be zeroed out. And what we have left is f of 0 is a of 0. And this is what I'm going to do. I'm going to try to figure out all these coefficients. I'm going to try to figure out all these coefficients right here. So at f of 0, we're going to get everything zeroed out behind this, and it's going to be equal to a to the 0 times 1, or a to the 0. Now, let's find the derivative of this. Let's find the derivative of this function. So I could look at a series and take the derivative of the series. It's not too hard. You can see I'll take one derivative of this just to give you a feel of it, but mainly I like the concrete polynomial terms on the right to really make sure I'm taking the derivative and kind of make a little better sense of it. But there is the idea that I can do this in an infinite series, because if I take this derivative, x to the n, well, we multiply by n, so we're going to get an n, an a to the n, and we'll subtract 1, so it'll be x to the n minus 1. And I have two choices here. I can take the derivative of every one of these terms, and I'm comfortable doing that because that's what we've been doing a lot in the last two calculus classes. Or I can plug and chug n is equal to 0 and n equals to 1, and it'll create a very similar, or it should be exact same thing. So let's just come back up here. What's the derivative of this constant times 1? Well, remember, this coefficient is just a value, so this is a constant, so that first derivative is 0. What is the next derivative? What's the derivative of a sub 1 to x to the first? Well, that's going to be just the a sub 1. This derivative right here, it's going to be 2 times a sub 2 x to the first. And the next derivative will be 3 times a sub 3 x squared. Okay, and then so on and so on and so on. Don't forget, this is an infinite. Okay, but I'm just going to look at the partial parts here. Let's go ahead now and plug and chug a 0 into the function, the derivative of the function. Let's plug and chug an f of 0 there. Excuse me, I wanted to put a 0 there. Hang on a second. Let's put a 0. Let's plug and chug a 0 in there. So if I put in the 0, okay, again, 0, don't have to worry about that one, plus a sub 1, okay, so 0 plus a sub 1, just a sub 1, and then plus 2 times a sub 2 to the times a 0. Okay, so this one's going to be 0 and this one's going to be 0, and you can see the rest of them are going to be 0. So now I have that the first derivative is equal to the first coefficient, or the second coefficient in the sequence, but the a sub 1 coefficient. Let's do another derivative. Okay, hopefully you get it, discovering a pattern of what I'm trying to do. I'm trying to figure out how I can take a function, a regular function, an f of x, and approximate it with this series. And to do so, I need to know the coefficients. And the second I figure out these coefficients, then I can get a polynomial. Okay. Again, I could take this derivative right here of the infinite summation here, the infinite series, but that's going to make it very cluttered, so I'm going to focus straight over to the polynomial. Okay, we got a 0 here, derivative of 0, or just bringing down the 0, 0. What's the derivative of a sub 1? What's the derivative of that constant? Well, that also is 0. So now, what's the derivative of this third term in this polynomial here? We got 2 a sub 2 times x, so the derivative of it is the 2 a sub 2. So the derivative of it is the 2 a sub 2. And then what's the derivative of the next one? Well, it's going to be 2 times 3, which is 6, but I want to leave it 2 times 3 because there's a later pattern in a later video you're going to want to notice. So here, let's use parentheses to make sure it's really clear. Yes, this is 6, but I want to show you the pattern, or I want you to imagine what the pattern will look like as we do this. So it's 2 times 3, a sub 3, and then I've got x squared degrades down to an x to the first. Okay, and then technically there's more. There would be more, but it'll have an x squared in it and an x to the excuse me, I'm trying to speak this one out. It's going to have more in there. It's going to have an x to the second, third, and fourth out here. But if I'm plugging and chugging 0, and I'm going to get the, this was a second derivative. That's a little bit of a mistake right there. There's supposed to be just 2 marks right there. So this is supposed to be just 2. Second derivative. If I take the second derivative and I plug it 0 into it, let's see what it's equal to. It's equal to 2 a sub 2. And then 0 here, and then 0 on the rest. So what is a sub 2 equal to? Well, a sub 2 is equal to the second derivative at 0. We're centering this at 0 right now. Okay, we'll talk about centering it elsewhere in another video or another time. But I just want to talk about it centering at 0 and see what the pattern looks like. So, now we've got the series. We've got it all the way down, and we have now a sub 2. If you look, a sub 3, right here with this 6, and you can see the next derivative, if I was to take the third derivative, hang on, I'm trying to scroll down here. If I was to take the third derivative, then I'm just going to jump the gun because I don't like the video to get too long. Third derivative should be this 6a3, because the x degrades down to basically x to the 0 or 1, and then all the rest of them, when you plug and chug a 0, are going to be gone. And again, this is infinite, but I want to focus just on this one part to build the first part of this. Plug and chug in a 0 into that third derivative, okay, and you're going to get the 6a sub 3. So that means a sub 3 is equal to f triple prime, third derivative, okay, divided by 6. All right, let's see what I can do now. I'm going to scroll this a little more here, okay, and I want to show you what we can do with this. I'm going to first show you the Taylor polynomial now, because now you can see what a Taylor polynomial looks. The Taylor polynomial, okay, sorry, trying to get my cursor lined up, a little rusty, it's been a while. Whoops, better summations. Okay, the Taylor polynomial, okay, of this idea of making this an a sub n, we're going to center it at 0, but I want to go ahead and write in where I would center it. If I had a centering elsewhere, I would need to do this shift. And if you've been understanding basic algebra and how everything can be shifted with this x minus c, then this is just shifting the centering to another location. So I'm going to write out the full Taylor polynomial where it's centered at c here, but in a few minutes here I'm going to be focusing at c equals 0 when it means to be centered at 0. And you can see that from what we've learned, that a sub 0 is my plug and chug of f sub 0. So I'm going to write f sub 0 here, f sub 0. But the Taylor polynomial would say f at c, but we're going to be looking at it at 0. So I'm trying to build that full equation here now. Now the first a sub 1, what was that a sub 1? Following it out, that was the first derivative at 0. I'm going to again write the general formula for it centered at c. So this is the first the first, right here, coefficient, or the second coefficient, a sub 1, and that's what I'm substituting, that coefficient of x to the first. Right now I have a linear approximation. If you're familiar with Euler's approximation, you're looking at it basically. Starting point, slope change, delta x change. So this is also mx plus b in the heart of it. I mean, you could see the mx plus b got a starting point and a slope, and then a slope times x. So I want you to connect this to the previous things you've learned. Don't make this too brand new. It makes it too daunting. Again, writing out the formula, the second derivative, we found out the next coefficient was the second derivative, again at 0 for our part, but right now we're going to go ahead and write the generic formula at c, and this is times x squared, following it out, third one at c divided by 6x cubed. So right now I have a cubic four-term polynomial, and this would go on forever technically. That's the whole idea, that we start from n equals 0 here, go out to infinity, but we want to start with just small approximations and get a feel for it. So let's try one. This is a lot of beginning. I'm sorry if the video is getting long, but I want to be sure you're comfortable with this. So let's actually try one. Let's take a look at one of my favorite little functions to start with in this idea is sine x. Okay? And let's explore. I'm going to have to plug and chug a function at a c value or at a 0 value here. So that means I'm going to plug and chug a 0 into these terms and get a value. I'm also going to have to take the first derivative, second derivative, and third derivative, and I'm going to need to plug and chug some values and see where they're at. And that way I can actually get my exact coefficients. I'll have a constant, as long as it's not 0. I'll have an x value, I'll have an x squared value, I'll have an x cubed value with all these coefficients. That's the idea here. So trying to bring it all together. Let me do a little scratch work. I want you to understand. There's just some scratch work I'm going to do. First derivative is cosine x. First derivative is cosine x. Second derivative is negative sine x. Third derivative, again, just doing some scratch work. I'm going to have to do this to plug and chug to build my polynomial, okay? So my third derivative, it's kind of like making a little review sheet before we do this, is negative cosine x, okay? And my fourth derivative, okay, fourth derivative, just in case, don't know how far I'm going to go out with this one. When we write that, you shouldn't write it that way. That was a mistake. I want to show you the proper technique for that. That was a little silly. That was just a little bit habitual. I want to make that a little 4 here. So when you're saying the fourth derivative, you put a little superscript 4 right there, and that's what you're indicating. And we get our fourth derivative, and we're right back at sine x. You might have noticed there is a pattern to this. You might remember that from pre-calc days. Okay? So let's see. I need f of 0. I need it 0. So what I'm going to do now is I want to build a little list here. I'm going to focus at c equals 0. So that's what I'm going to plug and chug into the function. And I'm going to get my answers here. I'm going to get my answers by going over here and plugging and chugging c equals 0 into my function, which is really where the x is. Don't get too confused between these x's and the ones over in the polynomial. Remember, this is just my scratch work. I just need to be able to plug and chug some numbers. So when c is 0, what's f of 0? Okay, f of 0 there is 0. Oh, so my constant's 0. Okay, all right, at c is 0, what's the first derivative here? First derivative at 0. Okay, so the first derivative at 0, cosine at 0 is 1. Okay, what's my second derivative at 0? Second derivative at 0, that's the next one we're going to need. 0. Third derivative at 0. Third derivative at 0, that's the one down there. That's the last one I'm going to get to for now. Okay, and that one's going to be a negative 1. But if I was to go to the fourth one, it would be 0 anyways. Okay, so let's build a polynomial to approximate sine x. That's what we're doing here. I'm going to build a polynomial that will approximate sine x. So we started off that this polynomial will be f of x is equal to the constant 0. The first coefficient is 1, the first coefficient, so I'm going to make 1x or just x, okay? Second thing is 0, the second derivative is 0, so there is no quadratic term. Third one is a minus 1, that's substituting right here on top, minus 1 over 6 x cubed. And now let's go take a look at the two graphs. Let's see how sine x compares to the approximation of x minus 1/6 x cubed. So getting back to my little graph, I'm going to turn off the first two. I've already kind of built them. Just give me 1 second here. I'm going to turn off the first two and turn on now the sine x and the cubic. Here's sine x, and there is the cubic. I'm going to have to actually zoom out a bit because it's so tight between's the wrong way there. That graph is so tight, so closely together between almost what, -1 1/4 to 1 1/4. There is a big, huge region that we will actually later identify as how tight we are. We are within a certain distance between each of our y outputs, all the way around 0. And again, the idea with Taylor polynomials, if I actually centered it elsewhere, if I centered it at 8 or pi over 4 or wherever, then that's just a shifting of those graphs. And that's what it means when we come back to the formula when we say x minus c here. And I did make a mistake here. I very much apologize, man. That's a big one. Okay, it's almost big enough. I should redo the video. It should have been x minus c there, and it should have been, I'm sorry here, it should have been inside that quantity, x minus c. I'm a little rusty with this. I apologize. And this also should have been x minus c. And all I'm really trying to say is if you remember your polynomials and how they work, okay, then what we're doing is we're just shifting it to another point c, but we still have to get all these coefficients at that point so that we know that our slope, our concavity, our changing slopes, and all the rest of the derivatives are really close together and create an equation that's very tight. And if you were to take this polynomial and go out to infinity, that's what we're going to be showing in a later video or later in class. I'm David from Electric Teaching, and I apologize for the mistakes. I am a little bit out of touch with these, and I hope this has helped. Have a great day.